everyone. We are going to move into working on adding and subtracting radicals. And the really key thing here is actually something that we already know about. It's like terms. So you cannot add two things together unless they are like terms. And where you may have seen this before is 2x squared plus x cubed minus x squared. You can't combine x squareds with x cubes. So to be like terms, they have to have the exact same variables with the exact same powers. In terms of radicals, it's the same idea. You can only add or subtract two radicals if the radical part is identical. And if there's variables in the mix, then it's all of the above. Radical parts have to be identical. Variable parts have to be identical, or we don't do the addition subtraction. So we're going to try and start out fairly simple and work our way up to some pretty messy looking things. Square root of 2 plus 9 root 2. So really I just want to emphasize the thinking here. It's the same as with the x squareds. If you have two of these x squareds, whatever those are, and you subtract one of them, you're only left with one. So we can do this thinking where the coefficient represents how many of something we have, and we can combine coefficients. So if I have a single square root of 2, and I add 9 more square root of 2's, I'm going to end up with a total of 10 square root 2's. So this will be our thinking as it gets messier and messier. That's still the underlying thought process behind it. Next example, 3 root 7 minus 5 root 7. This is very much the same idea. If I have 3 of these root 7s, whatever number that actually represents, I have 3 of them. I take away 5 of them, and I will be left with negative 2 root 7s. So negative of those. Let's go ahead and throw in some variables and talk about that. It, in this case, doesn't change our thought process a lot. If I have 5 square root of x's and I take away 11 of them, that's going to leave me with negative 6 square root x's. But I do have a third term that I need to consider. I then want to add a cube root of x. And if you're comfortable, you can do this all in one step. And in fact, here we're really done. We did do it all in one step because square roots and cube roots are not like terms. The radical part has to be identical. So if you have a different thing under the root, or you have a different index in your root, the index is the 2 or the 3 that make a square root or a cube root, you don't combine. It's okay to leave separate terms if they're not like terms. In the same way that up above with this polynomial, we would have left that as x squared plus x cubed. It's okay that you can't add those last two things. Okay, let's look at another with 3 terms. So we have a 6 times the square root of 2x plus a 4 root x. Those radical parts are not identical, so I can't combine those. Moving on, I have a minus 3x root x. I do see the radical part matching with the 4 root x, but the variable part doesn't match. I have another x here that doesn't match the root x in 4 root x. So basically the only thing that can be different is the coefficient, that single number out in front. If anything is different in those boxes, we don't combine. So in this case, we actually can't do anything. Our answer is that it stays exactly as is, which I don't think you'll see a lot of, but I just wanted to make the point that any difference in there is going to cause trouble. Okay, last row, I have a 3 root 8y plus a 2 root 50y minus a 7 root 5y. And initially I'm thinking I'm kind of out of luck because none of those radical parts match. But I want to remind you that sometimes you can simplify roots. So we should be trying to extract a little bit before we give up on this completely. The y's I'm not going to get to do much with, but I can split up the 8 and I can split up the 50. I think I'm pretty stuck on a 5. It's not a perfect square and it's prime, so I can't split it up. But as a little bit of side work, 8 is 4 times 2, or you can split that out more and say there's a 2 times 2 times 2, so that pair can be extracted. So I'm going to leave the 3 out in front. I will separate out a root 4, and I'm left with the 2, and I'm left with the y as well. I did not get rid of the y. For 50, I'll write this above, I can split that up into 25 times 2 times y, and I can do even better. I can make that 25 5 times 5. I think that's my prime factors. So I'm going to split off any pairs that I have. So I will leave the 2 out in front. I'll split off a root 25, and I'm left with a root 2y that I can't simplify. I don't do anything with the 7 root 5y, but I am going to go ahead and do the square roots that I can. So square root of 4 is 2. 3 times 2 is 6, root 2y. Square root of 25 is 5. 5 times 2 will be 10, root 2y. And then minus 7 root 5y. So here I get to combine the first two. They ended up with identical radical and variable parts, but the last one has to stay separate. I can't combine a root 5y with a root 2y, so I will make this a 16 root 2y. I had 6 of them, I added 10, that's 16, minus 7 root 5y. And that's it, I'm done with that one. Okay, just one more, and it's messy. I have an 8 root 2p cubed and a 3p root 18p, and that doesn't look great so far. The radical parts are different, and the variables outside of the radical also don't match up. The 8 does not have a p, and the 3 does. But I'm going to see if I can simplify, so don't give up without trying. I know I didn't try on the one right above this, but there was nothing to extract there. I was just kind of building up the idea about not combining if they're not like terms. So here, I can split this up. The 2 is prime already. In fact, I'm going to save that for last. But the p cubed I can split up. That's a p times p times p times 2. So I can take out 2 of those p's. And then 18 I can split up. 18 is 9 times 2, and the p I'm going to be stuck with. 9 I can do better is 3 times 3, so that is a perfect square. So I will leave the 8 out in front on this first one. I'm going to separate out a root p squared. As you practice this, if you're getting really comfortable, you don't have to write this in between step. If you can say, I'm going to take the square root of p squared and get p, go for it. You can jump right to that. If you find yourself making mistakes at all, come back to doing it the long way. I'll leave the negative 3p out in front, and I'm going to split off a root 9, and I'm left with a root 2p. So the root 2p part is looking promising. I do like that. The radical parts are now lining up. Oh, don't mind my pen. But I don't have a perfect match yet. So let's see. The square root of p squared should be p. There is potential for some trickiness there. The truth is, when you take the square root of p squared, you actually get the absolute value of p. But for the purposes of what we're doing here, let's just assume that our variables represent positive numbers. We can get into that trickiness a little bit later on. And then for the next term, I'll have the square root of 9 is 3. Which I can multiply by this other 3. So I'm going to have a 9p root 2p. And in fact, I did get like terms out of all that mess. The p's match up, the square root 2p's match up. So now I can say if I have 8 p root 2p's and I take away 9 of those p root 2p's, I'm left with negative 1 p root 2p. And as usual, you don't have to write the negative 1. You can just put that minus sign out in front. All right, so this should pretty much do it for the variety of things you're going to see. Let me know if you get in any trouble with these. Otherwise, we'll move on to mixed operations. We'll combine addition, subtraction with multiplication, and deal with a little bit of mess that makes.